So once more, good morning, everyone. Today we are going to talk about the balance of momentum and its specific implementation into a finite element program. We rely on the notation that we used in previous courses. We will only go through this in a kind of broad sense. So we're not going into the details how to derive, for example, a weak form. The weak form of the balance of momentum will be our starting point because we expect you to know how to derive a weak form based on the local statement or a statement defined in either reference or current configuration of a certain differential equation on your own. However, we will derive the weak form later in this course for the balance of energy, just because this you might have not done in any courses before, but for the balance of momentum, we will directly start from this weak form. So if you're not familiar with this, make sure that you at least have yourself a recap on previous courses where you have done these derivations. Further, we will do everything in, or most of it in index notation. So index notation you should be familiar too. The advantage here is that we can directly translate this to our code, as index notation is kind of the same or leads to the same expressions, formulas that are required to deal with vector and matrix fields in the code. But I'm sure you're aware of this as well. Additionally, we will focus on a so-called folk notation. So at a certain point, maybe even in equation 2, as I see, we will introduce a stress tensor vector, for example. So don't be confused about that. You have probably used that before. However, I will give you the proper definition, of course, but just that you know what I'm talking about. There is just a different kind of notation to it. Don't worry. Anything else? Yeah, so we will derive today the balance of momentum in the full form. That means we will include the dynamic terms for a boundary, for a body force, using the acceleration, and also we will use a viscoelastic material law. I've written here already, we are focusing on linear theory only. So the material law, the constitutive equation we will use is Hooke's law with an, so of course the constitutive tensor as you're used to, but with an extension. So there is a kind of damping matrix involved as well, which is then multiplied with the rate of the linear strain, so that we have some damping in our model. Okay. Anything else? I don't think so. Okay. Okay, so far we have introduced some, I have introduced here the weak form of the balance of momentum. As I said, this should be familiar to you. And what information do we get here? The weak form is actually a function which depends on a field u and a field variation of u. So the field u is our field which we will discretize in terms of degrees of freedom. So this is like the unknown that we are solving for. And we have introduced variation of u here, which is our test function. Recognize that at this point, those are like vectorial fields continuously defined over the body B. With respect to the linear theory, we know that we make the assumption that there is not much difference in the current configuration or the reference configuration, and therefore we only refer everything to the reference configuration, or simply speaking, we just don't care about any configuration. So B here is our body domain, and in here you can already see we are integrating over the body B. The next term here is integrated over the surface of the body B, partial B, also denoted here by dA. Furthermore, we have sigma as the linear stress tensor. We have epsilon as the linear strain tensor. X dot dot is the acceleration. U display. X dot. No. Even though it's not included here, this is of course the velocity. B So B is our body acceleration. That means we have a load, or a load acting on our body as a volumetric load. So for each volume of the body, this load is applicable. And we also see that this is integrated here as well over the body itself, also multiplied with the density. So that will lead exactly to the actual body force that we observe in the body due to acceleration. However, sometimes we refer to this vector field B as the body force. So as you see here, B as written in this formula is not a body force. It's actually kind of a body acceleration, or it is an acceleration, definitely. However, if you hear the term body force, usually this is what it refers to. Okay. And the last thing, T bar. T bar is our traction vector responsible for external loads. How big is the leg I got the information there's a lag between what I write and what you see. So maybe I'm just trying to disconnect once and connecting again. So I hope this solves it a little bit. Otherwise, there's not much I can do. I'm sorry. But you will be provided with the recording. So I hope this is possible for you. It is possible for you to follow. However, most of it, what we are doing today, should be familiar to you. Okay, regarding the traction vector, we see the traction vector here appears on this part of the weak form. And we use this parts to differentiate between the so-called internal part and the external part. No? Here we go. As you are already aware, we will implement in our finite elements just the internal part, because the finite element program usually takes care of the external part in terms of nodal forces that we apply in our scripts or input files for a simulation. So we generally don't have to implement the external part. There are a few exceptions, of course, if you're dealing with more complex boundary conditions, where you have to actually evaluate integrals over the surface, or if you have non-conservative loads, like loads that follow the motion of the body, nothing that you have to care about actually, then this is required. But for these reasons, the only loads that we are dealing with are introduced in terms of nodal forces. So this part is then evaluated by the finite element program, and the internal part is what we have to implement. Okay, the last aspect that I want to highlight here, of course, is that the weak form is actually supposed to be equal to 0, and also recognize that here is a scalar 0. So the weak form is a scalar expression. Okay. Okay, so here we have the internal part of the balance of momentum of the weak form already in index notation. So as a quick reminder of this index notation here, we have this indexes I here in this case, which will indicate that we will sum over all same indices. That means we have here all of a sudden a vector sigma, what I introduced before. This is like the Folk notation sigma. I'll introduce that in a minute. And we have a Folk notation vector for the variation of the strains, the linear strains here, also having the index I, and we will sum up over those i's. Same holds for the second part here regarding the dynamic terms. All of a sudden, I changed the x dot dot for a here. I hope you can adapt to this. The critical point here is that, of course, all the i's must be of same length, which is not exactly true here. So let me change this, or I leave this, because otherwise this will destroy my destroy my script. But of course, at least for the sum, which is then applied to each of these parts here, must lead to the same scalar properties. Okay, I guess this is a good idea to introduce this Folk notation. So sigma I is equal to okay, and here we are. You've probably seen those before. So the Vogt notation sigma is a vector with the main diagonal in the first entries and then followed by the off-diagonal ones. Of course, sigma, the linear stress tensor, is symmetric because of the balance of moment of momentum or balance of angular momentum. This you were introduced in continuum mechanics, if I'm not mistaken. So therefore, we only need to store here the 1/2 of the off-diagonal tensor. And the same notation basically is applied here to the linear strain tensor or its variation. So as we are going through the derivations, we will also see the Vogt notation of the actual strains, the actual linear strains. And this follows exactly the same notation. So the only difference with respect to the stress notation here is that we have 2 times the off-diagonal part here just for our formulas to work out. This whole Vogt notation thing is actually something that is just supposed to help you with implementation. So of course you could also deal with the full tensors here introduced, but the caveat is that then in the end you have to deal with even more indices. You have to deal with 4-dimensional fields, and this can be more difficult to implement. Therefore, people decided to use this notation just for simplicity. Okay. So in terms of the finite element method, if we as we aim to implement these formulas in our finite element scheme, we approximate this absolute integral here, or this analytical integral, by the sum over all elements. So, of course, we have introduced here our first approximation, because if you apply the discretization to your body, the body might have a complex shape with curved boundaries or other things. And basically what we're doing, if we mesh our domain, if we use a mesher to do so, the mesher tries to adapt to these curved shapes as good as possible. In case of a quadrilateral domain, if you aim to discretize this with quadrilateral elements, this can be done perfectly. But just to account for the fact that this is not possible in any case, this would be an approximation of the actual geometry. And as the geometry is approximated, also the integral therefore will not be perfect anymore. In the end, we get this sum over all internal weak forms for each element. And this is like how we used to introduce these formulas to the finite element method. We implement for a single element a function that performs this computation, and then the finite element program will take care of summing all of this up. Or in the end, actually, this is not summing up the scalar weak form, but assembling element vectors and matrices. Excuse me, with the question here, you need to be a little more precise, especially the second word, like FOK.
Zasha, I mean how it's spelled, folk, or like the spelling.
The spelling of what?
Folk notation, folk.
Folked. This is like so. Okay. So getting back, the thing that we need to focus on is in computing this part for one single element. And as the finite element program will apply this to any element, this works out in the end. So we are now thinking about implementing G internal for one element. And the next approximation that we introduce to approximate this integral here over the element domain is numerical integration. We have talked about this last time as well. And the idea is to approximate this integral over an element's domain by the sum over a certain set of integration points. Also with respect to the discussion that we had last week. So I introduce here the word Gauss integration, and this is due to the specific integration or quadrature points that we use, which are based on the Gauss-Legendre scheme. So we will have a sum over all these integration points. We will have our integrand here evaluated at these points, multiplied with a certain weighting factor, which is also part of the integration point set, and multiplied with the determinant of the Jacobian. The Jacobian I will introduce a little later. However, you should be aware of both this scheme as well as what the Jacobian is, which appears in our isoparametric concept. This is nothing else than the Gauss points are defined in xi and eta, and so we are integrating over xi and eta, our parametric space, and determinant of j is like the chain part that goes dx by dxi. So you have like switched the integral domain from the physical space to the parametric space, integrate in the parametric space, and push it back to the physical space. If we apply this scheme to our internal element-wise weak form, we are just asked to evaluate everything inside the integral at our integration points GP Of course, outer we have the sum. And one thing that I missed to say is that the determinant of the Jacobian is also evaluated at each integration points. So this depends a little bit on the finite element that we are using, whether Jacobian is constant even or depends on the parametric coordinates. However, this must be also evaluated in the parameter at the integration points itself. Okay, so on the finite element level, we introduce an interpolation scheme. Which renders this formula for any vectorial quantity. So I will not write down this formula again and again for each vectorial quantity that we are facing. Right here, you can see we have as a vectorial quantity, for example, the variation of u, right? And what I'm given here is the displacement vector ui. So this is like the same formula, the same scheme. You should be also aware of this anyways. But the novelty here might be that we apply this scheme, of course, to also the acceleration vector, for example. We will not apply this scheme to BI. So BI, as I said, is like the acceleration that we have for each fraction of mass in our body. So we will treat this as an input parameter. To give you this simple example here, usually we use this for modeling gravitation. And as gravitation is just constant, actually in the whole space for our experience here on Earth, and therefore we will not include this as a more complex function. So BI will not be interpolated. Also take notice that we are using here the two-dimensional space, just because this is what we're going to implement. The same formulas would technically work out in 3D. You have probably seen that. There is one more thing when it comes to interpolation, which is the interpolation of our strain tensor. So let me write this down here once in full length. For the linear strain tensor in Vogt notation, And there we have our beloved B matrix. So let's compare this formula to the interpolation of a vector here. So if we have the vector field and we want to express the vector field, like actually always in terms of nodal components, because I think we have talked about this in the last exercise. So of course, at the finite element is defined by a set of nodes. And at these nodes, we imagine that we have the quantities as degrees of freedom available. And if we are thinking about using this integration scheme now, we are asked to evaluate these formulas at the integration points, which lie inside the finite element domain. And therefore, we need to somehow get quantities that are available on the nodes at the inner domain of our finite element. And therefore, we use these interpolation schemes. So n here is, of course, our, like starting with this, n here is our ansatz function. Also, this was discussed last time, if I'm remembering correctly. So the ansatz function are defined, or there's within a finite element, there is one ansatz function defined for each node. And there is also one displacement vector defined for each node. Displacements will remain our degrees of freedom for this kind of equation. And then we have this multiplication here. So we multiply a scalar ansatz function with a vectorial displacement vector, and we sum up over capital I. Capital I is by notation an index for nodes referred to one element specifically. Now a little bit more complex when it comes to computing here the linear strain tensor in Fock notation. And for this, we don't use here the single shape function itself, but we establish this matrix here, which will be named B matrix in the end. And this is designed carefully so that if you carry out the matrix multiplication, which is implied here and also stated here in index notation, you will get by the formulas exactly these quantities. Comma x in this case means we have derived the shape function with respect to x. So the physical coordinate. So let's take care on this more specifically. Sorry. Okay. So once more, for repetition, we have this mapping between the physical space and the parametric space. So I see there was a question. Oh, yes, you're right. Thank you very much. So I actually missed here one row in the interpolation matrix. So now I think it's correct. Thank you. However, I'm not a professor. Thanks for the promotion, but I'm not there yet. Okay, so getting back to the shape functions, the shape functions are defined in xi and eta in our parametric space. All of this stuff was discussed last exercise, so please refer back to this. However, now we get to how to derive the shape function here with respect to x and y, because as the shape functions are a function of xi and eta, we have a problem here. So the solution for this is we introduce j, ij. So that's our Jacobian in index notation, I and j. And we can compute this. So it's basically, J is basically the derivation of our nodal coordinates. These are the coordinates in the physical space, like literally these coordinates here, with respect to the parametric space. And this is obtained by interpolation again, but using here the derived shape functions with respect to the parametric space. And this is absolutely easy to do, as those are really almost linear functions. We call them bilinear because there's a dependency in xi and eta as well. So those are easy to derive with respect to its arguments xi and eta, and those are used here in this interpolation scheme to obtain the matrix J. Further, we need the inverse. Okay, let me don't fall in the trap here to give you the inverse in the wrong notation. But of course, you know how to compute the inverse of a 2x2 matrix. And this can be used to obtain then the shape functions derived with respect to xi and y, x and y. So that would be in this fashion. We have our shape functions derived with c and eta again and multiply them with the transpose of the inverse of j. So I'm not brave enough to give you the detailed metric expression here without some proper backup in front of me. However, this index notation here implies the transpose that we actually have to introduce. And that would lead our shape functions derived with respect to x and y. And with this in hand, we can actually compute these B matrices that we need to compute our strains, our virtual strains or variation of the strains, our test strains, however you want to call them, and our strain rate tensor in Fock notation as well. Okay, so far for interpolation. We have left here with using this expression for the internal part. And maybe I continue here on the new page. Okay, so now we insert these interpolation formulas in our equation here. And we use this interpolation in this first step only on the test functions. And therefore we exposed the test quantities defined at the nodes, like variation of ui here is a vectorial test discretized at the nodes of the finite element, which only appear to be a function when it comes to interpolation with these B matrices. Same or with this B matrix to obtain the virtual strain and this shape function here to obtain the virtual test field. Further, we can recognize that we have twice here the summation with I, and due to some algebraic rules that you're all aware, in this case, we can take the sum out of the expression here and just apply it to the whole expression in the brackets. So we have sum over all integration points, sum over all nodes I. Like so. Okay. Arriving here is kind of an important part because from here we will switch to our understanding of the finite element method to introduce the element vector. We will take care of these additional quantities here, which do include which are actually formulas of our degrees of freedom when it comes to deriving the stiffness matrix or element matrix. Okay, so at first, the finite element vector. There are many names for this, like right-hand side vector or residual vector. I will use, or I will try to lean towards element vector here, and the definition is like so. Okay, so remember, and if you don't remember, please refer back to what we've discussed last time, that the finite element method will establish a system of equation, and under the general assumption that the system of formulas that we aim to solve, like the differential equations, are nonlinear, we apply a Newton scheme, at least most of the time. That means we have used the Taylor expansion, and then we get our equation evaluated at the current position plus a tangent, and we can reformulate this to solve not for the actual degrees of freedom, but for an increment within the Newton scheme. Further, last time we have discussed that you have this equation in terms of, or including here, the variation of u in a way that you can get rid of these variation of u, like we canceled them out in the equation last time. And to account for this step, it's just easier to write, for me at least, to write it in this way. So we take our weak form here, even in terms of each element just, and derive it with respect to our nodal test functions to obtain the right-hand side vector or element vector here. Okay, hope I can squeeze this formula here enough. Think that should do. Okay, so we see here that we used to describe this element vector in terms of per node and with a small I, so in terms of our spatial directions. For one element, let me put this here as a node. The whole vector looks something like this, or not something, but exactly like that. So we have a vector which is of length, spatial dimensions, x and y, or to be more precise, this refers to our unknowns. So as we have an unknown displacement in one direction, x, and an unknown displacement in y direction, this is why we got 2 entries here per node, as we have 2 degrees of freedom per node. And the node index here runs over all our nodes of our specific finite elements. So n would be the number of nodes that we have in the finite element, which will render 4 in case of our quadrilateral element. So what we get here is an expression. If we follow the derivations further, we get an expression for this part. So hope at least some of you remember, for your FEM implementations, you used to fill up this vector here in another loop over all nodes so that you can add these parts step by step. And this is also what we achieve with our derivations here now. This is something that you should also get back in your mind for this course, because when we actually implement our coupled problems, that would mean we have, in the end, we have 3 degrees of freedom per node. We have the displacement vector with displacement in x and y direction, and we have the temperature at the node. So that means if you think about this guy here, that we don't have 2 entries, but 3 entries. And this is not that much of an issue or unusual when it comes to our right-hand side vector. You would just use this I here to run over 3 and not over just 2 indices. But in case of the stiffness matrix or element matrix, this will render differently. And you will see that this matrix has certain properties, which we'll talk about later. So there is something to discover here when it comes to coupled problems. So please make sure that this concept is somehow familiar to you again. All right. So now we can actually perform these derivations, and we see that we derive here with respect to variation of ui. And we see we have a variation of ui in here, and we have a variation of uik in here. So yeah, so the of course you're all masters in doing differentiation, and with index notation, this renders here 2 Kronecker deltas, which just slightly shifted indices. I hope this is clear to everyone as well. And if we apply this to the formula, so now we have the derivation variation of uk with respect to ui. There we go. Yeah. Okay, so of course with index notation, you have to take care that you don't make any mistakes here. And as you just recognized, I switched from I to O here, because this I introduced here on in the beginning actually would conflict in this notation. You might remember that I was stuck here in the beginning when I recognized that these I's here run from 1 to 6 and those from 1 to 3. So this required a correction at this point. So maybe a little bit unlucky, but now that we've talked about it, I hope it's clear to everyone why this is the case. Also, this enforces you to keep your mind at attention all the time, because this is non-trivial what we are doing here, right? Okay. Simplifying that further, we arrive at this expression for the right hand side or element vector. All right. This is, of course, one of the targets that we will have to implement in the finite element. And you can already see that it will be possible for us to implement this. So we have talked about how to compute the shape functions. These are supposed to be known in terms of psi and eta. GP. And as psi and eta will render the position of the current integration point that we are evaluating, we can be sure that in the sum over GP, so the sum over all integration points, we are knowing the current coordinate of the integration point. So we can compute the scalar here for each of the nodal Ansatzfunctions. Further, we can, by knowing this, we can compute our Jacobian here and also its determinant and its inverse to compute here the derived shape functions, which will lead to a definition of this B matrix. So for each node, we are able to compute this matrix. Further, we will talk about how to compute sigma, but as you all know, there's a constitutive equation given. And once you have the strains computed, and in this case, the strain rate as well, which will be done through the B matrix, this is discussed like here. So we are able to compute these. We can also compute the stresses. The accelerations here, which will turn out in the end to be a function of our nodal unknowns, our nodal displacements. We will use the Newmark scheme, and we will see later in the implementation that you have already had this done when we implement the mass spring oscillator problem in the very beginning. We will apply the very same structure here to our finite element implementation. And last but not least, the weighting factor here is known as well. So this is actually, in a few words, possible to compute. Next would be the finite element matrix or stiffness matrix or tangent matrix. Once more, many words for that, but you know what this matrix is used for because you remember precisely our derivations from last exercise. During this Newton scheme that I outlined a few minutes ago, you have to apply a certain tangent to the function that you search the root for, which is in a perfect sense the consistent derivation of this function that you search the root for, derived with respect of the unknowns of the parameters of that function. So this leads to the expression for Kij, which is the right-hand side vector or the element vector derived with respect to all the unknowns. Recognize here, we have introduced a second index for the for nodes and a second index for dimension. And all of this, I think you have also derived in more detail in linear finite element method. This turns out to be the case just from math, because what we will do next is we will introduce our interpolation schemes here, also in terms of functions that depend on our degrees of freedom. And as those are multiplied with the further interpolated test functions or test properties, we have to account for this product by introducing here a second index for the nodes, J. Okay, so I guess this is a good idea to start with the introduction of the constitutive equation. That might take a few minutes. Okay, definition of the stress vector was given before. I think you have also seen this matrix before, the constitutive matrix for Hooke's law, written here in terms of the Lamé parameters lambda and mu, for which you will find formulas on Wikipedia and of course many standard textbooks. Mu is actually the compression modulus in this case, while lambda is just a different parameter introduced by these kind of expression for constitutive equations. And both, this is the important message, can be computed from the Young's modulus and from the Poisson's ratio that we as engineers are most familiar to work with. So we will definitely use these to describe the material of our finite element, E and Young's Poisson's ratio and Young's modulus as input parameters, and then you are asked to implement the formulas to compute lambda and mu. And to be honest, Wikipedia is just a very well illustrated source for that. Okay, so finalizing this equation, we obtain here our sigma Fock notation vector to be computed from this constitutive matrix. So it's a simple matrix. There, most of them is most of it is zero, except for those entries here where you have to insert the Lamé constants once you computed them. And this is our strain tensor in Fock notation, which was introduced before. This, however, is just the rate independent form of the linear stress tensor. We will use here the rate dependent form. So I just introduce an additional term here for the computation of sigma, which involves also the strain rate. Okay, so that has the same size as the constitutive tensor C introduced here above. And we introduce a material parameter, eta mu. Sorry, I'm running out here a little bit, and the mu looks different for me. I'm running out a little bit of Greek letters. So this would be a damping parameter. Which is also like a material parameter and will be introduced to the finite element as an input, just as Young's modulus and Poisson's ratio. I introduce here both because today we will focus only on, or we will implement only the steady state case, so the non-dynamic case of the balance of momentum. And your task will be for the next exercise to implement the dynamic form of the balance of momentum, which we will derive here, but not implement later on. However, this will be the formula that you need to implement for next week. This is the formula that we will implement today. And you can see this is like an additive term here. So that's rather easy to do. Of course, derivations have to be done further, which will be introduced some more complexity. Okay, so that's our constitutive equation. Further, we have to focus on time integration. According to Newmark. So I will just repeat formulas that we have not only discussed before in this course, but also implemented before in this course. Remember the first exercise with the spring mass oscillator. This is exactly the same scheme as in the finite element method. This is, or if I think about this program that we wrote, we have had the single mass oscillator implemented in a separate function, which is treated analogously to a finite element function. So you have been entered there with a certain set of history parameters, like the previous displacement, the previous acceleration, the previous velocity, and some new displacement. And for your finite element, this will be exactly the same case. You will be provided by the finite element program with certain values stored in a history field vector. We will talk about this later. And then you're asked to perform this Newmark integration scheme, just as in this very first program you wrote, so that you can make use of it also in your finite element. However, let me just repeat here the formulas that we used for the implementation earlier in this course. So we had here any quantity Okay, so these formulas, as I said, we have discussed before. The bullet here means that we can insert any quantity that we like, because we will use the very same formulas also for the temperatures later on, therefore this general scheme. And the dot above means first derivation with respect to time, twice a dot, second derivation. So if I use, instead of the bullet, our displacement vector here, I would read this function, for example, as u dot dot, which is our a, is equal to, inserting u again, un plus 1. So that's our current displacement. Current displacement is also our degree of freedom. The dot here is our un, so our previous value of the degree of freedom. Bullet dot n is our previous derivation of our previous, is our displacement derivation with respect to time, so velocity of the old time step, and the same applied here, which is our acceleration of the previous time step. All n values are supposed to be known and constant. For today's derivation, I need only the acceleration. Therefore, we can already prepare a certain derivation here to use it later on. For your homework, you will need to apply this kind of differentiation for the velocities. So pay attention. So I know down in my derivations, I will be asked to derive acceleration ij with respect to uji or jj even. For this, I can use the formulas. So this is the formula for the acceleration. Derived with respect to u, jj. Okay, now let's insert the bullets here, as I've done in a very confusing way before, just in words. So dot n plus 1, that means this is our degree of freedom. That means I can insert here u, and as this formula should lead an aij, I would need uij in here. Same for this, but this is of course the old value. And analogously, I can proceed also for the acceleration here. So remember once more, these are quantities known and they are just constant. Constant means with respect to the current degrees of freedom. So whatever our degrees of freedom will become at the equilibrium state in the current time step, it will not change the result that we obtained for the last time step. And so these are constants. And if I derive the formula here with respect, differentiated with respect to uji, so our degrees of freedom just with a different indexing, I can see that these constants will disappear, just as a constant disappears in standard differentiation. So the first simplification would lead, and let me drag here this factor of the equation just before it. And derive it or what I'm left with is just this is just uij with respect to ujj, and this we have done before is in index notation nothing more than a Kronecker delta ij. All right, so once more, this guy here vanishes in the differentiation because any n value with respect to any u is like a constant with respect to a parameter which is 0. And also to say this again, you will be asked to do this for the velocities for the implementation of the viscoelastic material. Okay, so with the expression for the acceleration, the constitutive law, and already this differentiation that we have just derived in hand, we can proceed with the element matrix. Oh, this is not the correct formula. I want I want it this way. And at this point, I'd like to stress once more that if you think about this equation with I and j here on the left-hand side, that means if you imagine the same concept that we discussed for the element vector, how you compute just certain coefficients of it at a time, this is also applied here to the stiffness matrix. Okay. So the first thing we do is we insert the constitutive law and the interpolation for our accelerations here. And here I am just using the non-dynamic part. What you will have to do, of course, is using the dynamic part in here. Okay. So the stresses here are asked to appear with an index O. Oh. So I use here OR and R times BOI plus. So that's our constitutive law, and now we can insert our interpolation And for the acceleration, we have as well. Okay, so here we have, of course, just still I in place. And the next part, I'm sorry for this messy equation, but simplification is straightforward. So as for the index I, we will drag index j in front of the equation. And then we apply our differentiation. That means if we look at these two terms here individually and derive it with respect to ujj, ujj can be found here in the same form. So that will lead our Kronecker delta in term of 1 again. And then we have in this term here our aij, and there we have a different Kronecker delta. However, this derivation here was provided here before, except that in this case, we have used different indices. And with this, we arrive at okay. So there was one mistake I made by not reading my own formulas here correctly, which is at this point here, I already introduced GI. By performing the differentiation here, or RI, by performing the differentiation with respect not to all, like a flattened vector of all nodal tests, but with respect to the nodal tests at node I immediately get rid of the summation that I took in front of the equation here. So up to this point, the sum over I is actually correct, but by this differentiation here applied, I get rid of this at this point actually. Okay, that means we are starting here without it. Like so. So at this point, we are deriving with respect to j. The sum j here is still valid because we haven't applied the differentiation. Here also, this is still okay, except that the I was not here from the very beginning. And now as we apply the differentiation with respect to j, we also get rid of this sum at the, in front of the whole equation. Also, here is a hidden summation within the brackets. And that would lead somehow in this, if I apply differentiation here, I would derive this term with respect to u and this term here with respect to u. So A somehow depends on u. We have discussed this before, but B does not. B is a constant. So here is my second mistake. So for B, we get rid of it. And we are left with this expression for K. So let me check the final result. I missed another thing because here this is not simply the Kronecker delta for this differentiation, but we have used or we have experienced a factor here. Like so. And now it seems like these formulas align. Okay. So I'm just checking whether I missed something else, but I don't think so. Anyways, beside this dynamic terms that we've taken into our residual here, into our element vector, this is like the standard element vector for linear elasticity in the steady state case. And we have just derived the tangent matrix, including some dynamic terms here. But this is the only this term we only need in the steady state case. So for today, without this term, Okay, so as a quick summary of all these derivations, we could say the following. For implementation of linear elasticity, in the steady state case, that means no dynamic terms, we have this expression for the element vector and that expression for the element matrix. This is what we will deal with today. I will provide you with the implementation of this. And for the next week, you are asked to prepare the same element with some derivative, or let's say like this, the ones that really want to shine, implement it. But you have to do the derivations for this tangent matrix here in the dynamic case on your own. That's for next week. Okay. So as a next step, we will take a look at first the technical question: how do we apply a finite element or how do we program a finite element for FEM and how to use it? And today, just in case with the linear elasticity form, which will be provided today. Do you have any questions so far? Okay, then I will stop the recording for now.